All right, non-functions. So functions that fail the VLT. So that the question is, how do we differentiate curves that fail the VLT? So if it's called a function, the implication is that it passed the VLT. And the implication is then that you should be able to get y by itself and take the derivative using the product rule, quotient rule, power rule, chain rule. The word curve is used intentionally, and the word curve implies that it does not pass the VLT somewhere, and it's not possible to get y by itself. And so we need something called implicit differentiation. Implicit differentiation. All right, so what's the opposite of implicit, like vocabulary, linguist-wise, linguistically? What's the opposite of implicit? Explicit. Okay, if something is explicit, it is clear. It is, direct. So explicit functions come in the form of y equals. Okay, that's what makes it explicit. It's y equals blank. You can put it in your calculator, you can graph it, you can differentiate it. And so then in that case, rules like power, product, quotient, all apply. Chain. So an implicit function those are such where you can't separate y from the rest of the problem. Okay, you can't get y alone. At least not easily. And so then you would use the method of implicit differentiation. To do that, we need both x prime and y prime to do implicit differentiation, or we need both dx dx and dy dx. So again, that notation lends itself back to our two founding fathers of calculus, either Newton or Leibniz. Newton was the prime guy, Leibniz was the fraction differential guy. So you need both of those in order, since you can't get y alone explicitly, you need both of those. So I'm going to show you kind of a real basic introductory example that could be done either way, but my argument is that implicitly will be cleaner. All right, so differentiate the following. 2x cubed minus 3y squared equals 8. I would like to compare and contrast with you the difference to hopefully make my case that implicit is sometimes better than explicit. So I would like to do explicit with you first, which is the old way, and then I want to show you implicit, which is the new way, or a different way. To do explicit, what do you have to do to the function first? Get y alone. All right, so let's get y alone. So that would be negative 3y squared would be 8 minus 2x cubed. Divide everything by negative 3. So that would be 2x cubed minus 8 over 3. And then take the square root. So y would be equal to the square root of 2x cubed minus 8 over 3. That would be the old way, where you have to do a bunch of algebra to get y by itself. Yeah. Then you're going to take the derivative. Oh, by the way, this fails the VLT because it's got a plus and minus square root. Okay, then we take our derivative. So we'd have dy dx. And we would need the power rule on the radical. So that would be plus or minus 1/2 times 2x to the third minus 8 over 3 to the new power of negative 1/2 times the chain rule of 6x squared. Not an attractive answer. Valid, not wrong, just not maybe as clean. So let's compare that to the implicit way. Don't bother getting y by itself. Just take the derivative of 2x cubed, which is pretty easy. What is that? 6x squared. And because you're taking the derivative, dx would follow that because it's the application of the chain rule, which will simplify. It'll reduce to 1, but we just get in the habit of doing that. Minus, then we'll take the derivative of 3y squared, which is 6y, but I also need dy dx. And then equals the derivative of 8, which is 0. Dx is 1. And so instead of getting something alone first, like in the other way, the old way, you get y alone first and then take the derivative. Here, we take the derivative first, and we get dy dx alone. So negative 6y times dy dx equals negative 6x squared. So I just move the 6x squared to the other side, and then I divide both sides by negative 6y. So I get x squared over y. And that's the derivative. Isn't that much cleaner than the old way? They are not wrong. We just are looking at more efficient and a cleaner way of doing it. Okay, any questions about that? All right, so let's try it again with another function that we're only going to do it one way this time. That fails the VLT again. So let's do find the second derivative, find d2y. And we're going to find that second derivative for the equation 2y equals x squared plus sine y. Now at first glance you might go, oh, but I can do the old way. I can get y alone really easily. Can you get y alone really easily? You can get one of the y's alone really easily, but what's the problem? There's still a y on the other side too. So implicit is going to be the best way here. So we'll take the derivative of 2y, which is not just 2, but is what? 2 dy dx equals, all right, the derivative of x squared is 2x dx dx. And then the derivative of sine y, which is going to require the chain rule because it has an outside and an inside function. So the outside derivative is cosine, and the y variable is left alone. And then we tack on dy dx. So remember, take the derivative first, and then work on getting something alone. I notice that there's the dx dx disappears, leaving me with a dy dx on both sides. So what I would want to do is gather all the dy dx terms on the same left side of the equation. So I'll have 2 dy dx on the left side, and then coming to join it would be a negative cosine y dy dx. So I'm bringing that over so that I have like terms, leaving me with just 2x on the right. Since dy dx is common to both of those, I can factor it out as a GCF. And so on the outside I would have dy dx, and on the inside 2 minus the cosine of y, and then still equaling 2x. And then I'd finally get dy dx alone. So 2x over 2 minus cosine of y. So the work, the key part of implicit, in explicit, you do the algebra to get y alone first and then take the derivative. In implicit, you take the derivative first and then do the algebra to get dy dx alone. So we've now got dy dx alone, except I didn't just ask you for dy dx. What did I ask you for?
Second derivative.
All right, so now I need to do the process again.
Can we just do quotient rule?
Now I can just do quotient rule. So d2, to show the second derivative, would be the quotient rule. So the bottom is 2 minus cos y times the derivative of the top, which is 2 dx dx, minus the top, which is 2x, times the bottom, which is 0 plus the sine of y dy dx, all over 2 minus cosine y quantity squared.
Why do we need to use like the implicit differentiation again?
Because I've got two different variables. I've got x and I have y.
Got it.
Okay? I don't have just a single variable. If I had a single variable, absolutely. If it was 2x over 2 cosine minus cosine x, but I've got two variables. So what happens to the dx dx? Okay, it reduces. What happens to the dy dx? Ooh, I replace it with what dy dx was that I just found. Okay, now, it very well could happen that is gonna clean something up for me. Like, you make that substitution and sometimes something really great reduces. So let's see what we get. Okay, we end up with, we've got 2 minus cos y. I'll put a 2 in front of that. 2 quantity, 2 minus cos y, minus 2x sine y times another 2x over 2 minus cos y, all over 2 minus cos y quantity squared. Now look at the numerator. Right now it looks a little messy, but what might help me out? I've got 2 times the quantity 2 minus cos y, which doesn't really have a denominator other than 1 right now. And then I have 2x sine y with multiplied, and it does have a denominator. What would I need to maybe help me out? A common denominator? Yeah. So if I could make a common denominator here, and if I could bring 2 minus cos y as its denominator, and then square that, now I have a common denominator, which is going to be helpful to me in simplifying this. So I'll have 2 minus cos y squared now, minus 4x squared sine y, all over the common denominator, 2 minus cos y cubed. because I have a single 2 minus cos y as my the denominator of my numerator, and I can combine that with the cube, with the 2 that are in the denominator. I think that's probably as far as you'd want to leave it. Take it. That's the second derivative.
Wait, is it cubed or squared?
It is cubed now, because I had one of those quantities in the numerator, and then 2 more in the denominator, which makes a total of 3 for the cube. Okay, last one. Write a tangent line through the point -1, 2 along the curve. Notice the word curve. Curve means it's not a function. X squared plus xy plus y squared equals 7. That's some kind of ellipse. All right, to write a tangent line, you need 2 things. You need to know the point and the slope. We already know the point, so then our job is to find the slope. We're going to find the slope implicitly by taking the derivative of each piece. All right, so all together, derivative of x squared. Oh, I'm sorry, I copied my notes wrong. That should be a subtraction on xy. Okay, derivative of x squared all together. 2x times dx dx. All right, minus parentheses. Please use parentheses when you're doing that. What do you need to take the derivative of xy? The product rule. So that will be x by itself times dy dx plus y by itself times dx dx plus y squared. The derivative of that is 2y dy dx, and then the derivative of 7 is 0. So I have a couple dx dx's, which are 1. What should I do with that negative out in front of the parentheses? I should distribute it. So I'm going to have 2x minus x dy dx minus y by itself plus 2y times dy dx. So I notice that 2 of my terms have dy dx and 2 of my terms don't. So I'm going to take the 2 that don't and move them to the other side of my equation. So I'll have y minus 2x on the other side. So I added y to both sides, I subtracted 2x. Now I'm going to factor out the common dy dx, leaving me with negative x plus 2y equals y minus 2x, and that can get divided so that I have my dy dx quantity being equal to y minus 2x for the numerator and 2y minus x for the denominator. So that's the value of the derivative. If I want to know what the slope is, I take the point, -1, 2, and I plug it in. So 2 for y, -1 for x, 2 for y, -1 for x, which gives me 4 in the numerator, and it gives me 5 in the denominator. So I get 4/5 as my equation, or my slope. So y minus 2 equals 4/5 for the slope, x plus 1, done.